Hello and welcome back to the second part of a lesson on section 5.7 topics. And here we're going to move into some of the trig functions that we've yet to work with in terms of integration. And you probably realize that some of this will have to do with logarithms because that was kind of the first part of this topic. We already know that the integral of sine is negative cosine, again, simply by an anti-differentiation understanding. We also know that the integral of cosine is sine. And we always have the plus c on an indefinite integral. But what about tangent? Well, now that we understand the integral of 1 over x is log of x, we can change tangent to our typical sine over cosine. So let's do that. So here's a little bit of a derivation. Let's derive this. I'm going to think of this as the integral of sine of x over cosine x. Well, guess what? I can now use u substitution. I can let u be the denominator. Du is going to be its derivative, which is negative sine. So now putting all that back in terms of u values, this is going to be the integral. Cosine of x is just u. The dx sine x, if we use that whole substitution, would be negative du. I'll just put the negative out front. Well, this, of course, is negative log u and then we put the u back in, we get negative log of cosine. So the integral of tangent is negative log of cosine. Of course, we're still going to have plus c. Sorry, that's all squeezed in there. But negative log cosine of x. Now you may remember some properties of logarithms that allow us to put this coefficient negative into the exponent spot, which would make this 1 over cosine, which is secant. So you could say the log of secant, but this tends to be the one that we use. Now, along those same lines, the integral of cotangent, we would do kind of the same type of thing, and we'd get negative log. Sorry, not negative log, just the positive log of sine. And again, you can go ahead and maybe establish it the same way I tried to derive this one. But instead of sine over cosine, it would be cosine over sine. So maybe I'll let you work through that one. Now, the next one's a little tougher. Let's get to secant. In order to find secant, again, we may start with 1 over cosine. But if we tried to use this same u substitution, we wouldn't be able to adjust it in any way. So actually, this would be a bad choice. You can try and try and try, you're just not going to get anywhere. So this is where the creativity of mathematicians always impresses me. I'm going to just decide to multiply top and bottom by secant plus tangent. So obviously, the integral of secant and the integral of this whole mess is the same thing because secant plus tangent over secant plus tangent is just 1. If we go a little bit further, we can make this secant squared plus secant tangent. Over secant plus tangent. Now, let's see how logarithms fit into this. It turns out that if I would let this be u, the numerator is its derivative. Because look, what is the derivative of secant? It's secant tangent. And what is the derivative of tangent? It's secant squared. So when all is said and done, this thing would actually be equal to the log of secant plus tangent. Now, we're in a weird situation right now. Typically, on in-class tests, you don't have to know these, so take some time to get very comfortable with them. Of course, you have your resources to refer to when you're working on worksheets, quizzes, and tests, so that's fine. But a lot of it is just recognizing that it exists, so you find it and you use it correctly. So let's practice using some of these new formulas that we have. First and foremost, I will find this integral. I think that's the one. And I do want to make it a definite. Well, we'll just keep it indefinite for now. In this case, it looks complicated. In the past, we might have let u be this everything under the radical, but then du is going to be so complicated, there's no way we can adjust. So this is where trig comes into play. It turns out that 1 plus tangent squared is just secant squared. So now, all I'm really doing is integrating secant squared. Put the square root of that. But the integral of the square root of secant squared would be the integral of secant. And the integral of secant, we now know, is the log of secant of x plus tangent of x. I hate to say it, but that can be a very simple problem. It's easy in terms of procedure. It's very difficult in terms of recognition. You had to recognize that this could be rewritten using a trig identity. And then after that, you needed to recognize that we now have an integral formula for secant. Up to this point and before today, that would seem almost impossible. Let's take a look at another example. I'll have to erase some of this. Let's get rid of the derivation part. Okay, in this example, we want to find the average value of f of x equals tangent of x on 0 to pi over 4. Now remember, average value of a function is an integral application. Maybe just as a quick review of this, if I would sketch tangent of x from 0 to pi over 4, at 0 it is 0, at pi over 4, you should know the tangent of pi over 4 is 1. So it's basically, you got that whole tangent function, but it's basically just looking at this part of it. Now remember, the average value, just as a reminder, is basically what height do I need to make a rectangle so that the area of that rectangle is the same as the area of this irregular shape. And we might guess, I don't know, it's about right in here. So that really is the average value. Now, how we find that, of course, is we just find the area under the curve from 0 to pi over 4 and divide by pi over 4, because that's the span. So if I write it in terms of a formula, this is what the average value would be. Average value would equal 1 over pi over 4 times the integral from 0 to pi over 4 of the tangent of x. Okay, so again, that's the area under the curve divided by the span. That's going to give you the height. But now we have to find out the integral of tangent, which we already know. So 1 over pi over 4, by the way, is 4 over pi. The integral of tangent we can see is log, negative log of cosine. Okay, and we're going to integrate that from 0 to pi over 4. So we get 4 over pi. If we put a pi over 4 into this x, we get negative log of cosine of pi over 4 is radical 2 over 2. Minus, if we put a 0 in for x, the cosine of 0 is 1. We get negative log of 1. Well, we should know that the log of 1 is 0. So basically, we get this, 4 over pi. Now, at this point, I probably would use a property that allows me to write, put this negative as an exponent. So it'd be the log of 2 over radical 2. But that's just going to be 4 over pi. 2 over radical 2 is just radical 2. And I can continue. 4 over pi. This is just 2 to the 1/2. So I can bring a 1/2 out in front. And the 1/2 times 4 over pi. So I get 2 over pi log 2 as an exact value. Now, towards the end there, I'm just having fun with properties of logarithms because you know I like to work with properties of logarithms. We should all enjoy that process, but not everyone likes the same things. So here's what we have up to this point. We now can integrate a huge variety of functions, realizing that the integral of 1 over x is log x, which we really already knew. It helps us tremendously with these trig functions, because before logarithms, we couldn't handle anything past sine and cosine. You might be wondering about cosecant. Well, cosecant is just going to be negative log of cosecant cotangent. Again, you can refer to that and look at it in the book and study that formula. I wanted to take the opportunity to review an application of integration, which is the average value of a function. So that's something that will come up again. But hopefully now with all of these examples and just by talking through them and maybe trying to give you some insight in the way I look at things, you're able to look at the problems in the problem set, make a decision for what you might be, and then go with it. If you can integrate it, great. If not, you either need to look something up, or maybe you made a mistake in letting you be a certain value. So good luck with the problem set from 5-7. Early next week, we'll take a look at our very last integration techniques before we kind of backtrack to section 5-6 topics. Enjoy the weekend, and let me know if you have any issues, and we'll see you soon.